this is part 2. Part 2 of finding the electric field due to a uniform charge distribution on a sphere, a shell. So in part 1, I mostly integrated. I got down to this crazy thing of an integral, and then I did that numerically. You could look that up in an integral table. You could do other methods to solve this integral, but I mean, it's not fun. Oh, it's fun. It's fun. I take that back. It's fun. Okay. But what I want to do now is to do a different method to find the electric field due to a charged shell, not using Gauss's law. Okay, we'll do Gauss's law is too easy to use in that case. So let's just see if we get the same thing. And the result we're looking for is the electric field outside the sphere looks like the electric field due to a point charge, and inside the sphere it's 0. Okay, so let's set up our situation and think about how we're going to solve this. And then we'll do it in Python. So here's my sphere. It has a radius r, a charge density sigma, and we want to find the electric field on the z-axis up here, some point z away. So what we did before was to say, okay, my observation location r is going to be the vector 0, 0, z, and then we said the charge location rq is just going to be some vector. I'll say that rqx, rqy, rqz. It has some xyz component. Okay. Now in the analog version, what we did was to write that in pseudo-spherical coordinates. Right. I wrote this in terms of theta, phi, and r, and for those 3 things. We don't need to do that now, but we do need that vector. And then if I have one single point right there, I can find r, the vector from here to there. It's just going to be rho minus rq. And then I can find the electric field due to that one point. I'll call it dE. It's going to be 1 over 4 pi epsilon naught dq over the magnitude of r squared times the unit vector r hat. Instead of integrating an infinite number of points, essentially is what we did, let's do a lot of points. So if I do that for 1 point, I can do it for 2 points, I can do it for 3 points, I can do it for as many points as I want. Right? So if I have a finite number of points, I just do it for all the points. So what I need to do is just to make some points in the shape of a sphere and then add up the electric field due to all those points. Should be easy. Now, how do you make points in a sphere in 3D space? There are a couple methods to do this. We want to make them uniformly spread. And so you can't just say, I'm going to go over theta and go over phi and pick points. It won't be uniform. So what I'm going to do is to do my favorite trick and use this function. In Python, in web v Python, random returns a number between 0 and 1. So if this has a radius of r, I can do r times 2 times random, not random, minus 1. And this will give me a number between negative r to r, right? Because this is going to be 0 to 2 minus 1 is, now it's going to be negative 1 to 1, and then I multiply it by r, and I get from negative r to r. If I do that for the x, y, and z direction, what I'll get is a cube of points uniformly spread. Now what I'm going to do after that is I can just say, okay, which of these points are inside of a sphere? So I'm going to look at the condition that the vector r temporary, we'll call it, the magnitude of that is less than r. And if they're greater than r, those are the points I'm going to throw them away. And then what I'll do is I'll do it again for another thickness, right? I want to make sure they're in this little shell. And if they're not in that shell, I'm going to throw it away. Once I have all those points, I can just calculate the electric field due to each point at the observation location and add it up. That's it. Okay, so let's do that, switching over here to Python. I'm going to give you the code, don't worry about that. So let's make some constants. So I'm going to say r is equal to 1. Just like before, I said k is equal to 1. That's 1 over 4 pi epsilon naught. I'm going to put it in there. And let's say sigma is equal to 1 also, just because I want to match it up with the other problem before. I'm going to go ahead and put my observation location, z equals 2. So r OBS is equal to the vector 0, 0, z, just like before, right? Now I have that as a vector. We could also put a sphere there. I'll do that. So let's call it OBS is a sphere. The position is going to be r OBS. The radius is going to be equal to, let's say, r over 50. Okay, let's just run that and see what it looks like. There, that was boring. Okay, now I need to start making my spheres. So let's say, let's make 100 points. And we can always, if we do 100, you can do 1,000, but let's start with 100. So n is equal to 100, and then lowercase n is equal to 0. This is how I like to count. There are more sophisticated ways to count, but I like to do it that just makes the most sense. We're not about programming, we're doing physics, right? So what if I do while n is less than n? And then you could say print n, and then you have to do n is n plus 1. So it's going to go through and just count up to 100. And there you go. It's 99, but it's got 0 in there too. So it is 100. Okay, so it's got 100 points. Great. Now what we're going to do is to make a sphere. So I'm going to make a random variable, a random vector. RT is going to be vector. I can actually multiply by r over here. R times, which is 1, that's fine. R times the vector 2 times random minus 1, 2 times random, not 0, random minus 1, 2 times random minus 1. So now I get between negative r and r in the x, y, and z directions. So once I do that, I'm going to make a sphere. So sphere position is equal to RT. Radius is equal to, let's say, r over 80. And let's make them yellow, just so we can tell them apart. Color is color.yellow. Let's see what happens. So there's my 100 points. This is the observation location. It's not in the sphere. See, it's in the z direction. There's your 100 points in a cube. It doesn't look like a cube, but if I go up to 1,000, it does look like a cube. There's your cube. See, it's a cube. Okay, so now what we want to do is just cut away all the points that are not in our spherical shell. I do need to determine the thickness of the shell. So I'm going to say dr is going to be equal to, let's say, r over 100. It's not an actual shell, right? Just like it's not a continuous distribution. That's fine. So what I'm going to do here is I'm going to make my RT. And then I want to check. I'm going to say, if is it between r and r plus dr. So if the magnitude of RT is, let's see, greater than r, and the magnitude of RT is less than r plus dr. Yeah. So if it's in between that region, then I'm going to make a sphere. If not, I'm not going to make a sphere. So I'm going to put this inside, and I'm not going to count it. And let's change this down to 100 just because I get scared. Okay, so there's my sphere. Look, it's an empty sphere. You can zoom in, right? So that worked pretty well. Let's make it 1,000. So you always want to do 100 just in case something terrible happens. So it made way more than 1,000 points, but it threw them away if they weren't in that sphere. So there's my spherical shell of 1,000 points. Now we can calculate the electric field due to all those points. Just for simplicity, what I'm going to do is to add all those points to up to a list. Okay, so I'm going to call it P's. So let's make an empty list. P's equals an empty list. I do need DQ too. So dq, let's do the same thing. Q, the total, I did this before, the total charge is going to be sigma times the surface area, which is 4 times pi times r squared. And so dq is going to be q divided by n. So each one of those charge has 1/nth of the total charge. So over here, I'm going to plot my sphere still, but I can take that out in just a second. I'm going to say PS is PS plus the vector RT. So it's going to be a list of vectors. That's all I'm going to have. So if I run that right here, there you go. Now, Python gets a little wonky when you start having too many things. So let's just take this off, and let's not draw the sphere. Okay, and then just to see if it's working, I'm going to print the length of PS, just to see if making sure things are working. So it's 1,000. So that's good. See, now I don't have all the visual stuff to worry about bogging down my computer because I'm also recording video and I don't have the fastest computer right now. Spoiler alert. Okay, so now we have our list. We can calculate the electric field. So we already have our observation location. What I'm going to do is to say, I'm going to go through that list and calculate the electric field in each one. So for that, I'm going to start off with an electric field of 0. And then I can add to that. So I'm going to go through the P's. So I'm going to say for P in PS. This will go through the list of PS and just call each one P, right? So I can do that. So the first thing I'm going to do is to calculate the vector R. R is going to be equal to ROBS minus P. P is just a vector. It's the vector location of a charge. And now I can calculate DE. I need more space here. So DE is going to be equal to K times DQ times norm R divided by mag R squared. Now I'm going to add that to my total. E is E plus DE. And I should be done. And at the end, I'm going to say print E equals E. And I don't even worry about the units. Let's go ahead while we're at it and print the theoretical Z component of the electric field. So ETZ is the electric field due to a point charge. So it's K times Q divided by Z squared. And let's print that. Print ETZ equals ETZ. Zero-ish, 3.19, 3.14. That's pretty good. Can we make it better? Yes, we can. If you can do 1,000, you can do 5,000, right? And I'm not drawing it, so Python's not going to really freak out that much. Let's rerun it. And now I get 3.148, 3.141, 10 to the negative 3.0. So it's pretty good. Every time you run it, you get a little different number because it's random, right? So sometimes you'll get better numbers, sometimes you'll get worse. If you were brave, you could go up to 10,000. I'm not brave. I've proved my point how that works. Okay, but what about inside the sphere? Let's do the same thing. Let's go inside the sphere. If I go inside the sphere, I'm just going to change this to Z is 0.5. The radius of the sphere is 1. Close to 0, close to 0, close to 0. That's the wrong answer. So it seems to work, and in fact, it does work. I mean, these are really tiny compared to the theoretical value of 50, right? So it is really small. And that's just 5,000 points. Again, if you want to do 10,000 points, do 10,000 points. But that's how to calculate the electric field due to this charge distribution numerically. I think it matches up well with the previous video. Watch both of them, and that's it. The link to this code is down below. The playlist for my whole electrodynamics down below. Talk to you later.